throughout various papers that I've done over the years with the emphasis on the GraphWorld paper.
But you want synthetic graphs that are faithful to the real world, so and that's the problem.
Well, yes and no, because it is also possible to generate synthetic graphs that go out of distribution of anything that is possibly seen in the real world, and that can be interesting too. But there is a particular challenge. You can want that, or you can desire a generation, like a distribution of graphs that is faithful to some real-world distribution. I will touch on that a little bit, but the main focus is just having the capability to do any kind of generation that you would like. Yeah. Okay, so a bit of history here. My dissertation at Chapel Hill was on graph clustering on weighted graphs. And in particular, we looked at weighted networks where the edge weight was conditionally independent of edge presence. So if the edge was there, then an edge weight would have some distribution, but if the edge wasn't there, then there would be no edge weight. And we were looking at algorithms that were iterative. And this was kind of like a style that my advisor favored, and I also came to favor via working with him. But the basic idea is this: you sample a starting node, like you can see there. I'm hopefully not blocking this part of the visualization. But then you test the neighbors of this node. Well, you start with the first order neighborhood, and then you run a hypothesis test on second order neighbors. And if they pass, then they join into the cluster, and so on and so forth, until this process converges. So it's an iterative algorithm that aims to extract communities independently rather than optimizing some global objective like modularity. Okay, so I won't go into the algorithm because that's not the focus of this talk. But I wanted to sketch out briefly what it was, because one thing we looked at when constructing this algorithm is, like, does it actually work, right? And so we can ask this question both theoretically and empirically. This theorem was a big part of my paper. I'm not going to go over the notation, but basically what it says is that under an appropriate weighted stochastic block model, the iterative procedure converges to the correct answer, given a large enough graph size with high probability. So this is the update function. This alpha is like your statistical significance value. This is the original. This is like your starting set. This is the graph, and this is the correct cluster. So it basically says if you start in the right space, you're going to end up with the right cluster under an appropriate generative model, right? So as with all theorems, the conditions are not fully general. And so to make a good paper, we also wanted to run some experiments. So at the time, there were not many available weighted network data sets that satisfied this conditional independence condition. So we built a weighted SVM. And this was like a new model that we proposed in the paper. Basically, you generate a standard SVM, and then you add edge weights that also have some preferential distribution within the clusters, right? And also at the time, when I was looking at these community detection papers, many of them, not all, but many of them were quite limited in what they actually experimented with synthetic graphs. So they would basically say, well, okay, we have these two populations of synthetic graphs. One of them has average degree 10, the other one has average degree 20. So at the time, I was like, I really want to know if this algorithm works. So I exploded the search space. And I said, listen, we're gonna test every single parameter of the weighted stochastic block model. We're gonna run it along an axis, and we're gonna plot all of these curves. Now, this had been done by a few papers at the time. So I'm not claiming to have invented this style of empirical analysis, but it's definitely not in every paper. And one nice thing you can see is that you actually get to see how these methods perform over the search space of the synthetic graph generators. So I'm not going to go into every detail of these plots because this is old work, but this is sort of like when I started thinking about this style of research. Okay, so fast forward to Google, I began working on graph clustering with GNNs. So in my dissertation, I was just working on community detection, which is a form of discrete graph clustering. But when I started working at Google, I joined the GNN team, which was kind of a rub because I was from a statistics network science background, and the GNN team was very graph ML. So I think that this talk actually kind of combines a lot of those flavors together. But as many of you may know, GNNs are neural networks that operate over graph structured data. So nodes have features, and the graph is basically a spectral filter that combines the features together and learns a predictive distribution on the nodes and often the edges. And if you have a graph readout, then it learns a predictive distribution on the graph itself. So for clustering, the GNN learns output node representations. So convolutions are performed over the graph, and you end up with output node embeddings after some number of convolutional layers. So then, though, for unsupervised graph clustering with GNNs, those output node representations are fed into a soft modularity function. And that soft modularity function was the point of this paper that I was working on with the GNN team at Google. So again, we had some theory that showed that this had good convergence properties, but we wanted to do more. And that was when I stepped in and said, hey guys, let's do this. Let's add some synthetic graphs to this paper. So that's what we did. So this is a standard stochastic block model. And this is the, okay, so the nuance here is that formerly we had just in SVM, right? In my dissertation work, we added weights to the edges. But in the GNN paradigm, as I mentioned, nodes have continuous features, right? And the goal is to, transform those features via the graph. So we simulated node features from a multivariate Gaussian mixture. And the mixture was defined over the predefined clusters that corresponded to the SVM in this case. But we also perturbed that system by decomposing the clusters into sub-feature clusters. So we wanted to test the case where the node features didn't perfectly correspond to the stochastic block model features. So we discovered widely varying trends of these unsupervised graph clusters against the synthetic model. I mean, some of these methods didn't perform, they didn't perform very well at all. DMON is our method. As you can see, it tends to outperform most of the other methods, but not always. And we were able to explore the cases where it did and didn't. One thing that was really cool that I saw is that in the SVM, and actually in many synthetic models, there's a spectral detectability limit of the clusters. And some of you may be familiar with this, but basically, given a certain cluster definition of a graph and the strength of the within edges versus the without edges, the detectability limit is the point where spectral clusters can no longer detect the community partition. And it turns out that our method actually started losing efficacy right at the detectability limit, which it was very interesting because our loss is crafted around the modularity metric, which has close connections to the very same spectral objective. So this method of varying the parameter of the synthetic model actually was able to expose that phenomenon. So all of this led our team to think about this synthetic problem more generally. So that was clustering with GNNs. It's an unsupervised problem. But of course, as many of you may know, GNNs are used widely for many supervised problems as well, including link prediction, edge property prediction, and probably the most popular, node classification. And GNNs, of course, feature many different types of architectures. Lots of different inductive biases can be used for certain problems. So this is a graph that you may all be familiar with, the Cora ML citation graph. In this picture, the nodes are colored by subfield. And this graph has been used, probably it's safe to say, thousands of times at this point, if not a few 10,000s of times across papers, right? So this is taken from the original GCN paper, Kiff and Welling, where they showed, increasing performance from deep walk and beyond. So anyway, the point of this slide is to say, we had so much success using synthetic benchmarks in graph clustering, we wondered if the same technique could be applied to GNNs in general to overcome some benchmarking pitfalls that existed at the time. So what are those pitfalls specifically? Well, let's look at the progression of work in the field. So this is the Kiffin-Welling paper, and basically this is the table from this paper, and of course it includes a line for the prior state of the art, right? And so on and so forth. Like every new paper comes out and it says, okay, we did better than the last paper, and so on and so forth, right? So the field is just really over optimizing to these few data sets that may or may not have a lot of nice variance in these graph characteristics. So like, what really is the field optimizing for? These were the questions we were asking, thinking about this problem. So we decided to sort of sketch out what we meant by this by plotting the benchmark data sets against the broader collection of network data that could be out there. And that broader collection, we actually just took from the network repository, which probably many of you are familiar with, probably more so than me. But we basically downloaded the 5,000 or so graphs from that collection. Most of them don't have labels and therefore are not as useful for GNN node classification benchmarking, but they are useful for computing graph statistics, which is what we did. So this is a very simple plot of the Gini coefficient of the degree distribution versus the clustering coefficient, the global clustering coefficient of each graph. And we see that there are some regions, right? Like I don't actually know what this region is, but it's probably some subset of graphs from the network repository, maybe like the biographs or the citation graphs or something like this. But what we saw is that the traditional benchmark graphs kind of like don't cover a lot of this space, right? So our question is, can we generate more of this space to see what results in papers actually generalize and which ones don't? So yeah, to go over this slide, the potential downsides of relying just on real world graphs are that the experiment results in the papers may not generalize. Similarly, researchers may be optimizing over time for these very specific graphs. And a side point here is that the Open Graph benchmark came out, sort of saying like, this is the new state of the art in graph benchmarking. But again, there's only about 10 very large graphs in that benchmark, right? So these are actually the OGB graphs, right? They're not Cora necessarily. So our question was, how can we test GNNs on arbitrarily diverse graphs? And we took inspiration from the graph clustering with GNN's work, and we said, hey, we'd like to convert these limited tables into wide property axes. So this brings us to GraphWorld, and this is basically the pitch slide, right? It's general synthetic graph benchmarking methodology. We use random graph models to benchmark GNNs on whole populations of data sets. It extends to any task in any synthetic graph model, and it enables us to discover new relationships between GNN inductive biases and graph properties. So these were my collaborators on the paper, Brandon, Brian, and Anton. And this paper eventually made it into KDD, which is where I met Ayan, and also where I met Tina remotely. I think you were present for a different talk that I did that was like related or something. But yeah, it was around the same time. Okay, I'll pause here. Are there any questions?
In some sense, you are preaching to the choir here.
Yes.
For Science Institute. So for us, like, how is your degree distribution, or how many triangles you have?
Yes.
Is really important, and we don't lump all networks together.
Mm-hmm.
I think the part that is interesting is not just the network structure, but you need labels, as we call them, features.
Yes.
And in fact, he said something along the line of transform those features via the graph, which to me sounded like the graph is a second citizen, like a second class citizen. Which it's for me, the graph is the first class citizen.
Right.
The features, who cares? But I can imagine, obviously, Google and other places.
Yes.
It's just the graph is a vehicle. You could take the train, you could walk, versus.
That's a very interesting point, and indeed, when I started working with the GNN team, so most of those folks also treat the graph as a first-class citizen. But the point of a graph neural network model is that every node has a feature, right? So if you were trying to predict a property of these nodes, you could just feed those features into an MLP, right? But the graph should be seen as, much richer information about the connections between those node features, right?
There's
and
relational dependency.
Exactly.
You're going to use the relational.
Yeah, and GNNs are basically, I mean, if you think about image models, right? A convolutional neural network on an image is just a GNN on a lattice graph, right? Because the pixels are next to each other, right? Exactly, yeah. So GNNs, and this is a perspective championed by, I think, Michael Bronstein over the years, but like GNNs are basically like geometric learning, right? So I think the graph is one citizen, right? And it can even be the first class citizen, but it's not the only citizen in like GNN land, I guess. And it was a shift for me too, because like when I did my dissertation, nodes didn't have features in my experiments. Right. The edges had weights, but when I joined Google, I was totally new to thinking of graphs in this way. And I mean, that's because when I joined Google, it was 2017, and GNNs were just still kind of becoming popular at that point. Yeah.
But like, if you think, I'll just push this point a little bit. If you think about like the solutions that people use for over smoothing or over squashing, which is like drop edges or add edges, like from a network science perspective, especially from a computational scientist, you don't do that. What do you mean? Like, Tina called Bob, and now you're saying Tina didn't call Bob? Or you're saying Tina called everybody in Boston?
I actually completely agree.
And so then it goes back to just transform those features via the graph to optimize this particular function. Like, I really don't care about the graph.
Yes.
Or, I want you to do the best on this vector.
I totally agree. I think it's a very weird thing. So this is a particular hill I would die with you on if some of my co-collaborators in GNN land were here, because there are people who work on this. It's like, how do we modify the graph to learn a better the functional distribution on the graph, right? And it's like, why would you want to do that? Like, I
can understand from statistics, right?
Yeah.
That, okay, this is the graph I observed, and there may be some noise in there, and I would like to get rid of some of that, and you may have some formal way of doing that, and I'm all for that. And we had Jean-Gabriel Young from the University of Vermont on Friday here, and he's done some great work on it. But not just cutting edges or adding edges to get some machine learning model to do 2% better on some accuracy measure.
Yeah.
So,
this is a super interesting conversation.
I don't want to derail your
time. No. It is a derailment, but that's not a bad thing, because I think it does kind of like work at the interplay between graph ML and network science, which is very much the core of this talk. Yeah. Okay, so just a very brief field overview here. There are sort of there were two areas of related work in this before we published the paper. One is that a lot of folks had written a lot of very comprehensive pipelines for benchmarking on real world data sets. And then the other works that I featured here are papers that have synthetic data sets, but they're not very general. They were sort of crafted for the purpose of that paper. So in contrast, kind of like combining the two ideas, we actually have a very general pipeline for synthetic data. And again, I hope to sort of show you how it can generalize to any graph learning task you're willing to implement, and that these data sets are tunable with interpretable parameters. So the formal setup here, this is really just a generalization of what I did for the graph clustering papers, right? The task can be represented as a product space over a triple: graphs, features, and labels. And as Tina alluded to, you need all three, which is not trivial, right? Most folks, if they're just studying graph algorithms, all they need is this. So you generate a stochastic block model, or you generate preferential attachment, and you see how your model runs. But for GNNs, you actually need creative and useful ways to generate the features and the labels. So secondly, getting to that point, you need a generator, which can be formally framed as a probability distribution on that joint space. And then to test stuff, you need at least one model that you're interested in testing, but of course you can have many models. And then you also need some performance metric. And the GraphWorld algorithm is given this task P and any given number of models and a metric and a number of samples that you want. GraphWorld can be implemented as a simple for loop. You just sample a given parameter set for the model, and then you sample the data set given that parameter set. So this is sort of like a hierarchical model. And then you actually run the models. So you compute what the models can predict. And then you record the performance metrics. And once you have done this, this allows you to draw curves like this, right? So our paper was really just formalizing this idea, presenting a system for it, and showing that it can be useful on 3 different GNN tasks, the main 3: graph property prediction, edge property prediction, and node classification. So here's an example of this. So let's say we wanted to run node classification with GraphWorld. A really great model for this is the stochastic plot model, right? Because in the real world, the labels of a node usually manifest in some cluster distribution. It doesn't have to be stochastic plot model. I'll get into a little bit of that later. But the SVM has been my best friend for like 8 years. I'm featuring it here.
But that's for social and information, right?
Yes.
Not for
yes, and it's also only for assortative signal, right? So you can also have nodes that organize into disassortative signal, or they can have just unique connectivity profiles to the rest of the graph that are neither assortative or disassortative, right? So there's a lot of work that could be done with more generators for this system. The metric here would be classification accuracy, because we're doing node classification, and models would be things like GCN and GAP, right? Yeah. That's awesome. Yeah. And GNNs are normally pretty good at generalizing beyond assortative structure, but not always graph clustering. So the important thing here is these 2 graphs can be mapped to an appropriate axis, right? So the homophily in this graph, you can assume I used some sort of force-directed layout here. You can see that the homophily is quite low. Over here, quite higher, right? So we basically generate a bunch of graphs, and then we align them on the axis according to some graph statistic, and then we can just compute these response curves. So yeah, these are old slides, and I repeated myself a lot back then, but basically this allows us to answer questions like how do GNNs respond to variance in these graph properties, and also where do existing data sets fall on the axes. I don't have to go into this too much. When I presented the paper, I was talking about like how this could be parallelized. GraphWorld is trivially parallelizable. That for loop can just be sent to a bunch of workers, as you're seeing in the screen. You basically need 2 things. You need like a model configuration, so search space for the models. You can do hyperparameter tuning within each worker. And then you also need a graph generator config. And this is really the novel part for us, because I was basically doing this by hand for previous papers, like saying, I want the SVM to go over this range. But we actually defined like a common schema for this in the framework. So basically you send both of these schemas to Google Cloud Platform, which is what we used for the paper. Your workers do all the work, and the metrics get aggregated, and that's how you get your results, basically. Okay, so we did this for node classification with the SVM. The labels were just the cluster labels, and the features were a multivariate Gaussian mixture. Very similar to what we did for graph clustering, but this time we were doing GNN node classification. So a few things that we saw. I'll start with the obvious ones. Feature center distance is how far were the node features away from each other in latent space, cluster to cluster, so intercluster. All models respond to that positively with a similar shape, but kind of with different carrying capacity, right? So we didn't I still haven't really like, I haven't really dug in too far about these results. GIN and SGC are down here. I think that's kind of interesting. GIN is sort of like it's more of a graph readout model. SGC is a simple graph classification. So it lacks a lot of the, high performance GNN features. So those two facts could possibly explain why these are trailing. And, MLP actually leads the charge here, unsurprisingly, because MLP only uses the features. And this is only about the features, right? Okay, P over Q ratio. This is a very confusing name for literally just the intra-cluster edge density with respect to the inter-cluster edge density. So the higher this is, the more homophily there is in the graph. And interestingly, there are sort of like three classes of models here. There are models that increase linearly in performance. There are models that increase logarithmically. And there are flat lines. And the flat lines make sense. The MLP flat lines on this because it doesn't use the edges, right? That's a really obvious one. The APPNP does really well. And this is a model that can basically traverse long distance over the graph. So there may be something to that, which is that like APPNP is very sensitive to the homophily signal. And here's another obvious one. None of the models respond to the number of nodes in the graph. And this is intuitive if you think about what GNNs are doing. They're basically looking at the patch of the graph and doing convolutions on some limited k-hop neighbor. So the size of the graph technically shouldn't matter. Now, that said, this only goes from 128 to 512. So these are relatively small graphs. I think if we wanted to throw a bunch of money at a GraphWorld experiment and we went all the way up to like 10,000 or 100,000 or even a million nodes, and we did some fancy things with the degree distribution, we might see some movement there, right? But we haven't done that yet. And on that note, very interesting stuff going on with the average degree. I think SGC is basically just smashing the node convolutions together. So as the average degree goes up, SGC is like super subject to oversmoothing. So that is our preferred explanation for this. And however, most of the other models go up with average degree, which is actually similar to graph clustering. A lot of graph clustering models get more information when there's more edges in the graph. And I think the same thing is true for GNNs. So I could go on, but I think, this is, we were fairly happy with what this was able to expose with relatively small graphs. And these experiments didn't cost too much on GCP. Any questions about these?
I think the thing which is great about this is that it shows you some of the inductive biases that your model has.
Exactly.
Even if you didn't think of it.
Yes.
It's like, oh, okay, the model is this,
right?
Right. Which you learn in like machine learning 1.
Yeah.
But you need to have some inductive bias, otherwise you cannot learn. And what is it that's being used?
Yes, so, totally.
Did you look at triangles? Because usually triangles go hand in hand with degree.
Yes, they do. So higher the degree, more triangles. So that's probably why we didn't look at it initially. And the other reason we didn't look at it is because we didn't have an explicit mechanism to generate triangles in a graph. And and we still don't, right? Like
long-standing problem.
So actually, it would be interesting to, given a fixed average degree of the graph, increase or decrease the number of triangles, right?
So actually, one thing there is this work called block two-level Erdős-Rényi model that came out of Sandia National Laboratory. They call it the Better model, BTPR. So what
excuse me.
What it does is it creates a bunch of dense Erdős-Rényi graphs, and then it connects them so that the degree distribution is what you wanted.
I see.
It's heavy tail. But when you want to seed it to actually get instances of graph, you give it both the degree distribution and the triangle distribution.
That's really cool.
And so it still doesn't give you this like degree versus average number of triangles, which is really what you want.
Yeah.
And it doesn't have the seeding for the features or the
Right.
labels.
Or even any clustering, latent clustering in the graph itself, right?
No, it
You're right.
doesn't. So those guys worked a lot on. So the guys is Ali Pinar, Sash Amandar,
Yeah.
Tammy Kolda were working on it. So, but it would be interesting to put in block level
Absolutely.
generator and see what.
Yeah, please send me that reference
Yeah.
after. Yeah.
Isn't all of the labels have the same distribution and unbiased one? And if you have bias, how do you calculate the accuracy? You do so you have 9% red labels and prove them just to all of the red 9% accuracy.
I see.
So do you have bias? And how do you deal with bias?
So for these experiments, I am pretty sure, although I'll have to check, that the clusters were basically the same size. So the sizes were homogeneous, right? For biased distributions, like maybe 40, 30, 20, 10, if you have 4 clusters, right, in percentages. Yeah, I mean, so accuracy will still tell you something, right? But like, you can really choose any metric you would want. AUC does correspond to this notion of like, if you take any 2 nodes from different classes, the probability that you place them correctly or rank them correctly is equivalent to AUC. So like, null performance is still 50% on this, at least in the 2-class scenario. But I mean, GraphWorld is very agnostic to whatever metric you would like to choose. So like, if you do induce bias in the labels, then it would definitely be good to choose a metric that accounts for that in some way. Yeah. Okay, so this was this was exciting for me because up until this point, up until this project, I'd only been looking at like one axis, right? So we thought, why not 2 and make some 3D plots? So there's a lot of things going on here. So first of all, this edge homogeneity is basically P over Q, which I showed earlier. And this is the average degree. So this is a great way to visualize the real graph world, right? This is the whole world of graphs that our system generated. And
well, it's not the whole world of graphs. You know, there would be a lot of people who will come after you with pitchfork.
It's the world of
eigenvalues. I got triangles.
Right. It's a 2D slice of the world. Yeah. And it's only the world that our system generated, yeah. Right? Yes.
Fair enough.
Isn't it in experiments so you leave available for the set GNNs needs features? That's not true. GNNs do need features. And you also assume this Gaussian distribution. Like
yeah.
So what even if you say, now you only show path.
Yeah.
You make some assumptions.
Yep.
This is not so you leave available features. Just look at what can you learn from it in the structure.
Yeah. So GNNs definitely don't need features. And that is basically another type of generator that could be input into GraphWorld, right? So we're not claiming to cover all situations of GNNs with this paper because there are just simply too many. We didn't look at featureless experiments, for instance. But this has actually been interesting to me because in graphs without features, you know, some people just add random features and then run the GNN, right? Some people add a constant feature, right? If you just put a univariate value 1.0 on every node, and then you run a GNN, an untrained GNN, you'll basically reproduce the cluster proportions out of that, right? So these are very interesting experiments that GraphWorld could run. But it is just a system. So like, you know, we didn't do any of that sort of thing. And to your point, a mixture of Gaussians is unrealistic. I agree. I mean, so is an SVM, for instance, right? Like, so, you know, that if you project the Cora features into a latent space, you get something that kind of looks like a mixture of Gaussians because those features are from regions of citation network that are all similar, right? So that inspired our choice of using a Gaussian mixture for that. And yes, for this 2D slice, we didn't look at anything related to features, but I mean, we could have, right? I could replace this average degree with the feature center distance and see how it looks. I don't want to move on. Yeah, but the reason we did choose these two is because we overlaid real world data sets onto this world, right? So let me describe what's happening here. You can see GCN, APPNP, and film. These are three different GNN inductive biases. They all have associated papers. And the z-axis here is the mean reciprocal rank of each model with respect to the 13 other models that we tried in the experiment for the paper, right? So this is not a performance metric per se, but it is the mean reciprocal rank of the model compared to the other models. So this hump or these contours actually reflect changes in rank. Like if we wrote a paper for every point in this in this graph world, this is what the rank of the model would be in the table, right? So what do we see? First of all, a lot of the classic benchmarks are really localized to one spot of this graph world, and furthermore, that spot is unique, right? So like GCN performs really well on the synthetic space that corresponds to these data sets, but it drops off in the region that is not populated by the existing benchmarks. Similarly, APPNP doesn't do well over here, but it tends to do well outside of that region. So what we liked about this plot is it kind of shows that GraphWorld is capable of generating these regions of the node classification task that where new stuff happens that we didn't see in the existing benchmarks, right? So like this was sort of the plot that convinced us like, okay, GraphWorld is actually doing something here. Now, everything that both of you raised is completely valid because these results are not on the real data sets. They're on synthetic graphs that match these real data sets in only these two dimensions. So if we plotted different dimensions, we might see something different. If we ran an experiment without graph features, it would also be a different story. But basically, GraphWorld is the tool for doing that sort of thing. Okay, and the point of this slide is you can also do graph regression with GraphWorld, but I'm going to skip it and move on to some more interesting stuff. Okay, a few notes here. So as I mentioned, GraphWorld uses, in the paper, we were only using small to medium-sized graphs. And if you really wanted to get super big, it would be more expensive and therefore less feasible. So that's a limitation. A disclaimer that I've already mentioned is that GraphWorld is agnostic to the task generator and the performance metric. So the experiments in our paper are just examples of what you can do with the framework. Furthermore, reliance on the same GraphWorld experiment over time will also cause this hypothetical phenomenon of researchers overfitting to data sets, right? So it's important to sort of like, if you're using GraphWorld, come up with something new, right? If you are coming up with a new algorithm, come up with a new generator and plug it into GraphWorld, basically. And then finally, as we've been discussing basically this whole talk, existing synthetic models are pretty simple, and there's a lot of work that can be done. So so this is sort of where I ended my talks in 2022, but we've actually done some work since then. So we worked with a University of Warwick computer science student to add some new generators to GraphWorld. And he very diligently and effectively implemented two existing models into the framework. So they're now on the GitHub page. So in addition to SVM, we now have LFR. And we also have this newer model from Kabam, called Kabam, which was introduced by Neil Shah, who many of you may know. He's a graph ML researcher working at Snapchat. And the Kabam model is basically an extension of preferential attachment to include cluster preferences. So basically, the limitations of the SVM, which are like, every cluster is basically Erdős-Rényi, those don't exist in the Kabam model. It's a little bit more realistic if you like preferential attachment. So we found that these three models, they produce the same clusters in terms of labels, but the graph characteristics within and between these clusters are vastly different. And these differences are sometimes borne out in the GNN performances. So, his work basically amounted to a workshop paper. It was accepted at GLB KDD last year. And if you're interested in seeing how the experiments went, please check out the paper. And then the second limitation I mentioned is GraphWorld doesn't do massive graphs. And it still doesn't. But we did write a paper with an intern who worked on a benchmark generator for massive graphs. And instead of, so this is very outside of the GraphWorld context, but I just wanted to mention it as follow-up work in the synthetic graph space. The goal here is actually take one big graph, million nodes, even 10 million, and make a synthetic copy of it. Okay. And now, obviously, you could just copy the graph, but for privacy reasons, you may not want to do this. So instead, we made the observation that GNNs operate on patches of large graphs. That's how they operate. So why not replicate the patch distribution? And that's what the student did. She worked on, she invented a transformer model for patches of graphs. And basically, this transformer model learns the graph distribution just from the patches, basically. And this allows GNNs to be trained on a graph with a similar patch distribution. And one thing that was really interesting is like, how do we actually show that this is useful? Well, ideally, if you, let's say you're at a company and the graph you have is proprietary, so you can't share it, right? But you can train this transformer model. You would want the GNNs that you train on the original graph to perform similarly on the generated graph. So that's what we tested. We took, so these five methods are methods for generating the private graph. And every data point corresponds to a train of a particular GNN model. So, for models M1, M2, so on and so forth, this kind of is like sort of a GraphWorld concept. You get a vector of performance measurements on a particular graph. And the empirical target that you want to match here is the correlation between these performance metrics on the original graph and the performance metrics on the generated graph. And we saw that for our graph, they hit the ideal correlation line a little bit better than most other models that we tried. So that was basically the main result I wanted to show there, because there is like a loose thread to some of the GraphWorld concepts. I will close with some future work that actually hasn't been done and relates to many of the questions asked today. Okay, SBM, as I've been saying, is a really great intuitive generator for node classification. And the reason for this is it's very good at simulating homophily. You can really control the homophily of the graph. And this is the signal, among other things, that determines the task difficulty for node classification. So for instance, in social graphs, birds of a feather flock together, so on and so forth. But this is not true for all tasks. So here's one example. So fake news detection has been a hot topic since at least 2016, if not before. And there were lots of papers that claimed that the cascade graphs that come out of social media, their characteristics can tell you something about whether the root node, what was being shared, is viral or not. Or well, obviously, I think like virality is actually a characteristic of the graph, but it can tell you something about whether the root node is like an inflammatory piece or not, right? Now, fake news is a version of inflammatory, but also so are rumors, right? And other things, hate speech, for instance. So these types of graphs are, first of all, small graphs. So it's more like learning a graph readout distribution similar to molecules. But homophily doesn't play as big of a role here. What does come into play are substructures, right? And in general, as shown on this slide, the ground truth distribution of these substructures for things like cascade graphs are not yet known. And the SBM doesn't cover this at all. Here's another example. Ground truth distributions are hard for molecules. It's non-trivial to generate molecularly valid graphs. I think a lot of people here are much more knowledgeable than me on this. I haven't worked in biological graphs at all. And there actually is, I think, some modern day work on constrained generation. So, one semi-open question maybe is like, are there parameterizable generators for molecules with realistic ground truth distributions. Because if they are, you can plug them into GraphWorld and have a great time looking at your models. So I'll end with that. I won't even go through the takeaways because I've already said all of them. But this was a really cool thing that an artist that works for Google helped us write for the Google AI blog post on GraphWorld. And there's a lot of links that you can look up. So that's it.
Are there questions in the room before I open it up to Zoom?
Yes.
Thanks for the great talk.
Yeah.
I'm just curious if GraphWorld has been used for hyperparameter tuning, where we're using a single model, different configurations.
That's an excellent question. I have always imagined that it could. In fact, I got like a quarter of a way through a paper on that exact topic and then abandoned it in favor of some other things at Google. So have you heard of GraphGym? Yeah. So GraphGym is actually kind of similar to GraphWorld in that like they generated a bunch of synthetic graphs and then they like said, okay, like choose the argmax of hyperparameters that perform the best over this gym of graphs. But what you could do actually is pre-train a GNN on this synthetic graph distribution. And not only that, but like, so most of the time you only have one graph. And when you do Bayesian hyperparameter optimization, you're searching through a space of hyperparameters. And this is a high dimensional space, right? What if you had 1 million graphs, right? Now you have a graph distribution space and a hyperparameter space. So that's a doubly joint optimization problem. That's the problem I was trying to solve. If you want to write a paper about it, you should, and I'd be happy to work with you on it.
Other yeah, actually, some of the stuff that so obviously that's an excellent talk. As I said, you're preaching to a choir here because like one of the things that we oftentimes do in network science is compare it to the configuration model.
Right.
It's like otherwise it's not real, which unfortunately machine learning people don't.
Not yet. We're trying to make it happen.
Totally, Michelle.
Yeah.
Yes. I'm glad that you have picked up that mantle. I've been talking about it for years.
Yep.
No avail. But given that we have some time, and I know that a lot of people are working now on large language models.
Yes.
You have shifted a little bit.
Mm.
Do you want to talk a little bit about what you're doing there?
Yes. So the main trend in graphs times LLMs right now, the combination of these two, first of all, it's very nascent, right? The main thrust in many fields is to get LLMs to recognize arbitrary data structures, right? So LLMs traditionally operate on text. So if you can convert your data structure into text, then presumably it can do something on it, right? So the papers that are coming out right now in graph learning and LLMs is essentially very early coarse-grained attempts to do this. How do we represent a graph as text? How do we fine-tune a pre-trained language model on such graphs for very simple tasks, right? Edge presence. I'm not joking. Look up these papers. It's literally like, here's a graph in text form. Tell me if there's an edge between Alice and Bob. And LLMs can't really do this because they can't reason over a list, right? So the challenge is, how do we represent a graph in such a way that an LLM can profitably reason over it and actually do inference tasks on it? So it's total greenfield right now. I was not involved with the early papers from graph mining on this because I was working on some other stuff, but we are working on a time version, a temporal graph version of some of these problems. So like, again, very, very simple tasks like which edge came first, right? These are actually very hard problems for LLMs to solve with low-hanging fruit representations of the graph as text. So I think that's kind of the state of the field right now. Yeah.
Go ahead.
Yeah, thanks for the talk.
Yeah.
of the P coefficient and the clustering.
Yeah.
So a basic question, but you're saying there's some caveat here that these aren't labeled feature graphs. I was just wondering if you had any comment on that, whether we can expect properly this, like where a certain graph lies on this we correlated with whether or not it has node level features.
I see.
Sort of assuming that this is there's no reason that graph in the top right corner, like have any more or less change in doing it ends on.
That's interesting.
Could you repeat the question online?
Yeah, so the question, and correct me if I'm wrong, but I think the question is are there regions of this space that are more likely to have node features associated with the nodes or labels associated with the nodes themselves? I think this is basically just a empirical question about which data sets are represented on the network repository. It's a fair and interesting question because there are lots of different domains represented on this graph. Like, as I said, I don't know what this is, but it's definitely some cluster of like closely related graphs. Could be bio, could be citation. You're making me want to check. But if it's bio, they're going to have certain features potentially. If it's citation networks, they could also have features. But the point I was trying to make earlier was that the vast majority of network repository graphs, just as a matter of fact, as a resource, they don't have labels, and therefore they have not been relied upon by the field. If they did have labels, maybe the field of GNNs would have a much richer real-world benchmark space to work with, and we wouldn't need GraphWorld. But I actually don't agree with that, because no matter how big your real-world benchmark space is, it's never going to cover all the graph properties you might want to test, right?
Let's see, there's a question in the chat. Do you see the chat?
Oh, I do actually.
Right.
Oops. Okay, so since the space of all graphs of a certain size is extremely large, generating synthetic graphs would also cover a tiny part of that space at best. What's your thoughts on how to best generate synthetic graphs? Yeah, this is true. So, you know, we're doing empirical studies here, and the full space of 512 node graphs is out of reach. That said, I think a lot of these graphs are, for all intents and purposes, exchangeable. So, you know, there's a whole subspace of graphs that have homophily equal to 0.4, right? There's a whole subspace of graphs that have homophily equal to 0.3. And even discretizing down to those points goes well beyond what is available in the real world benchmark space. So that's what GraphWorld does. It generates a sample from this full infinity space that you're talking about, which is high coverage enough to be useful and vastly outpaces what is available in the real world. So yeah, very, very well taken, point well taken that, you know, we can never generate the entire space, but depending on what